Ever wondered how AI models like GPT or BERT understand language so remarkably well? The answer lies in a revolutionary architecture called transformers. Today, we're diving deep into the technical heart of transformers, how they work, why they're a game changer, and what the future holds for this foundational AI technology. For decades, recurrent neural networks, RNNs, dominated natural language processing. But RNNs had a critical flaw. They processed text sequentially, making it hard to capture long-range dependencies. Then, in 2017, Google's research team introduced transformers, a model that abandoned recurrence entirely. Instead, they relied on self-attention mechanisms, allowing the model to weigh the importance of every word in a sentence simultaneously. This breakthrough enabled parallel processing, drastically speeding up training while improving performance on tasks like translation and text generation. Let's break down the transformers architecture. At its core are two main components, the encoder and the decoder. The encoder processes input data, transforming it into a series of contextualized representations. The decoder then uses these representations to generate output, such as translating a sentence into another language. But the real magic happens in the self-attention layer. Here, each word in a sentence is compared to every other word, creating a matrix of relationships. For example, in the sentence, the cat sat on the mat, the model learns that cat and sat are more closely related than cat and mat. This is achieved through query, key, and value vectors, which mathematically encode these relationships using dot products and softmax normalization. Wait, how does the model know the order of words? Unlike RNNs, transformers don't process text sequentially. To address this, researchers introduced positional encoding, a technique that adds sine and cosine functions of different frequencies to word embeddings. This gives the model a sense of position, allowing it to distinguish between dog chase the cat and cat chase the dog. But transformers aren't just about language. Their architecture scales remarkably well, enabling models like GPT-3 with 175 billion parameters. This scalability is thanks to the attention mechanism's linear complexity in sequence length, compared to the quadratic complexity of RNNs. Transformers aren't limited to text. Their success in NLP led to adaptations like vision transformers, ViT, which treat images as sequences of patches. By applying self-attention to visual data, ViT achieves state-of-the-art results in image classification. Similarly, models like BioBERT and ClinicalBERT adapt transformers to specialized domains, enabling breakthroughs in bioinformatics and healthcare. Even in reinforcement learning, transformers are used to model complex decision-making processes, demonstrating their versatility. Of course, transformers aren't without challenges. Their computational demands are immense. Training a large transformer model can consume thousands of GPU hours. Additionally, the self-attention mechanism's quadratic complexity becomes a bottleneck for very long sequences. Researchers are addressing this with innovations like sparse attention, where the model focuses only on relevant tokens, and efficient architectures like reformer and linformer. There's also the issue of interpretability. While transformers excel at tasks, their internal decision-making remains somewhat of a black box. So where are transformers headed? One frontier is efficiency. Models like DistilBERT and TinyBERT compress large transformers without sacrificing performance. Another is multimodal learning, where transformers unify text, images, and audio into a single framework. Companies like Google and Meta are also exploring causal transformers for real-time applications, such as chatbots and autonomous systems. Meanwhile, researchers are investigating how to incorporate symbolic reasoning into transformers, bridging the gap between data-driven and rule-based AI. Transformers have reshaped AI, but their journey is far from over. From their elegant self-attention mechanisms to their adaptability across domains, they've become the backbone of modern machine learning. As research pushes boundaries, whether in efficiency, scalability, or multimodal capabilities, their impact will only grow. If you're curious about the next big breakthrough, keep an eye on transformers. They're not just a tool, they're the foundation of tomorrow's AI revolution. Thanks for watching. If you want to explore the math behind self-attention or see how to implement a transformer from scratch, check the links in the description. Stay curious, and don't forget to like and subscribe for more deep dives into AI's most fascinating concepts.